so on. Go ahead.
Yeah, thank you so much again to the organizers for putting on this conference, and all the great speakers. So today, what I want to do is I want to talk about virtual crystals, promotion, and then also the cyclic sieving phenomenon. So basically, what this will be based on is partially work by Okado and Shimozono that we did together yesterday. And Mark Shimozono's talk, he mentioned how he met Professor Okado, and yeah, that's basically also how I got involved with working with Masato Okado and Mark Shimozono. So the work on virtual crystals is based on joint work with Okado and Shimozono. And then when I will talk about the cyclic sieving phenomenon, this is partially work based on work with Fourier and Shimozono. But the main work that I will actually talk about today is a preprint I wrote with Joseph Pape, Stefan Pfannerer, and Mary Claire Simon. So Joseph Pape and Mary Claire Simon, they are two current students of mine, and Stefan Pfannerer is a student of Martin Ruby in Vienna. And here's a preprint number that this is based on. So let me start with the motivation of what I want to talk about. So what we want to study are invariant subspaces of a tensor product of certain representations. And for us, since we are mostly interested in crystal bases, so it turns out that the dimension of these subspaces is actually given by the number of highest weight elements of weight 0 in the corresponding tensor product of crystals. Okay, so that's basically what we will be working with. So if something is of highest weight of weight 0, then these are basically singleton nodes in our crystal. And the symmetric group acts on these tensor products just by permuting the tensor positions. And one thing that Bruce Westbury showed in 2016 is that the action of the long cycle corresponds to the action on promotion on this invariant subspace. And we will use this using crystals. So I will define for you what the promotion does on the crystal, and in particular on these invariant subspaces or highest weight elements of weight 0. And then what I want to end with at the end is that given these highest weight elements of weight 0 and the promotion operator, we will actually get what's called a cyclic sieving phenomenon, and I will define that later on in the talk. But what you need for a cyclic sieving phenomenon is some polynomial such that if you evaluate it at certain roots of unity, you actually get the number of elements in a cycle. And this polynomial turns out to be given by the sum of all the elements of weight 0, like the highest elements of weight 0, graded by the energy function. So that will come at the end of the talk. Okay, so let me begin by telling you a little bit how these highest weight elements of weight 0 look like in various cases that I want to consider. So let's first look at a very simple case. So I'm going to look at type A1. So in this case, my crystal is just this very simple crystal. If I just look at the vector representation, so I just have an element labeled 1, an element labeled 2, and then the crystal operator F1 takes me from 1 to 2. So if we want to look at highest weight elements using the bracketing that I told you about in my first lecture. So remember that a 2 will be bracketed with a 1 if the 2 comes to the left of the 1. So in this case, here in this example, this 2 is bracketed with this 1, and this 2 is bracketed with this 1. So therefore, this is indeed a highest weight element, because I cannot act with an E1 on this. And it's also of weight 0, because it contains the same number of 1s as 2s. So this would be one particular such element, and here's another such element, because here the 2 is bracketed, this 2 is bracketed with this one, and this 2 is bracketed with that one. And these elements are in fact in one-to-one correspondence with Dick path of length n. So if I have n tensor products, then these would be Dick paths of length n. And how does that work? So if I look at the 1, I'm going to think of it looking from the right as an up step. So this one corresponds to an up step, this one corresponds to an up step, and then the 2s correspond to down steps. And since I have the same number of 1s as 2s, right, if I start on the x-axis, I will end up on the x-axis. So these will be Dick path. And also, I can't go below the line, because I always have to have more 1s than 2s if I, starting from the right, if I want to be a highest weight element. Okay, so that's a very simple case of type A1. Now let's look at a slightly more complicated case. Let me look at the vector representation for type CR. So in this case, my crystal is again so the vertices of my crystal are again single boxes. And now they can be filled with the numbers from 1 up to R and R bar up to 1 bar. And this is the crystal for type CR for the vector representation. So in particular, F1 takes 1 to 2, F2 takes 2 to 3, and so on. And then my FR operator would make an R into an R bar. So now let us look at what are the highest weight elements of weight 0. So if I take the second tensor product of this, so the weight in this case, an I in a box would have weight EI, I bar would have weight minus EI. So the way that you can get weight 0 is by having the same number of I's as I bars. And well, if you want to have a highest weight element, then I should also say I'm using sort of the opposite of the Kashiwara convention for tensor products. Then you have to start with a 1. And then if you want to be highest weight, well, you could follow this by a 2 or by a 1 bar. But if you want to be of weight 0, it has to be followed by a 1 bar if you have only 2 tensor factors. So there's one element of highest weight that is also of weight 0. And these elements, in fact, correspond to what are called oscillating tableaux. So how do we get these oscillating tableaux? Well, I'm just going to keep track, start like looking from the right, what the weight would be of my tensor factors up to a certain point. So I'm going to start with weight 0 or weight empty. And then when I add this particular element, that would correspond to weight a single box. And then when I look at both of them, I would be back at weight 0 or empty. So that's why in my oscillating tableau, I go from empty, single box, empty. If I look at the fourth tensor product, here are my 3 highest weight elements of weight 0. So you can check here that, right, when I have a 1, I also have a 1 bar. When I have a 2, I also have a 2 bar, and so on. So these are all of weight 0, and they're also all of highest weight. And then the corresponding oscillating tableau are given by these elements. So for example, for this one, right, I start at empty, then I add a 1. Then when I look at these two, the weight is actually equal to 1, 1. When I look at these cancel out, so I'm back to weight 1. And then when I look at everything, this will be again of weight 0 or weight empty. Okay, so those are the two ways of looking at these. Yeah, so in particular for type C, these will be in one-to-one correspondence with oscillating tableau. I want to look at one more example, namely the spin crystal for type VR. And here I'm going to look in this example just at type V2. For the spin crystal, the elements are given by arrays of height R, so R tuples of pluses and minuses. I mean R if we are looking at type VR, since we are here looking at type B2, these would just be tuples of pluses and minuses. And an F2 operator makes this top element into a minus. Then the 1 operator switches the plus and the minus. And then the 2 operator again makes this top plus into a minus. So you get this element at the end. Here I've listed the elements of highest weight of weight 0 for the tensor product of 2 such factors, and here for the tensor product of 4 such factors. And these are actually in natural correspondence with fans of dick path. So if I look at type BR, they would be in correspondence with R fans of dick path. So by an R fan of a dick path, I just mean a sort of a tuple of dick path such that they're contained in each other. So, or one is below the other. So in particular, how does that work in this example? So if I associate with the bottom row here, the white path, then I have a plus and a minus, or I have an up step and a down step. And similarly for the green path, which would be the top row, right? So I have up and down. And then you can see that for this last example, for example, the 2 dick paths are actually not the same. So the bottom row here would be up, up, down, down, but the top one would be oscillating. So up, down, up, down. So those would be, in this case, 2 fans of dick path. Okay, so what we want to do is we want to now analyze these elements in the crystal. So these elements, these highest weight elements of weight 0. And the way that we are going to do that is by looking at virtual crystals. And the reason why I want to look at virtual crystals is because a lot of things are already known for type C, and we are going to use certain embeddings of type B into type C to analyze these crystals. So let me now explain what I mean by a virtual crystal. So what you need for this is some embedding of algebra. So we are going to embed an algebra which I label X into some algebra labeled Y. So for example, one running example or a prototypical example would be to embed type C R into type A to R minus 1. And if you look at the linking diagrams, so type C, the linking diagram looks like this. Type A to R minus 1 would just be a line with 2R minus 1 vertices, but we are sort of going to fold this linking diagram like this, so that we actually identify the node 1 with 2r minus 1, the node 2 with 2r minus 2, and so on. And the node r minus 1 with the node r plus 1. Right, so we are going to identify these, and the node r is sort of on its own. So the maps or the data that we need to actually write down what our virtual crystal is, one thing that we need is this map sigma. So that is a map that takes a node in the Dinking diagram of type X, in this case type CR, and tells us what all the Dinking nodes in A2R minus 1R that are associated to this Dinking node. So basically it keeps track of this folding. So in this case, node I, in this case 3 of type C, is associated with 2 nodes, I and 2R minus I in type A. So that's what this map sigma is keeping track of. And then the node R in this case, in type C, is just associated to 1 node in type A2R minus 1. So that's why sigma of R only has 1 node associated to it. Then the other thing that we need to keep track of are what are called multiplicity factors. I'm going to denote them by gamma I. So gamma 1 in this case is equal to 1 for all of these nodes, and it's equal to 2 for node R. So that's the data we need to keep track of. And it turns out that there is an embedding of the root and weight lattice. So in particular, the fundamental weights associated to the algebra X under this embedding will be mapped to this sum of fundamental weights of the algebra Y. So we are summing over all the elements in sigma, and then we also multiply by this multiplicity factor. So now I'm going to define what we call the ambient crystal. I'm going to denote this by V hat. So this will be a crystal of type Y, and I'm going to denote the corresponding crystal operators by EI hat and FI hat. Okay. So this is just the usual type Y crystal. And now inside that crystal, we want to define what is called a virtual crystal. So we need to define virtual crystal operators. And these will just be products of crystal operator in V hat. So we are basically taking products, again, according to the sigma, and sometimes we also have to act with a particular E hat multiple times given by this multiplicity factor. So the way that we are now going to define the virtual crystal is as a subset of our ambient crystal, such that the crystal operators are what are called aligned. So these conditions here specify that the crystal operators are aligned. So in particular, if we have 2 simple roots that are both in sigma I, we want that the corresponding epsilon, so the epsilon just measures how often can you apply an EI operator. So we want that in both cases, you can apply the EI operator the same, or in this case, EJ and EJ prime, the same number of times. And the same for the fees. And we also want that both of these, so the number of times you can apply an EI hat operator, that has to be a multiple of this multiplicity factor. And if we have that, we can define an epsilon I and a phi I by, well, picking any representative J in this sigma I, and we take the corresponding epsilon hat in the ambient crystal, and then we divide by 1 over this multiplicity factor. So this will be an integer because of these alignment conditions. Okay, and then finally, what we need for a virtual crystal is we need that this subset that we are choosing is closed under these virtual crystal operators EI and FI. And if we have that, then the epsilon I and phi that I just defined is actually the maximal amount of times we can apply the virtual crystal operators to the given element. So here is a typical example. So let us consider again the embedding of type C2 into type A3. Then as my virtual crystal, I'm going to take B box tensor B 111. Okay, so the B vector representation of type C2 is given by this crystal graph, and the claim is that we can model this using a virtual crystal by looking at this ambient crystal of type A3. So we start with the highest weight vector 1 tensor 1, 2, 3 in here. And then we are going to apply these virtual crystal operators. So the F1 in this case is F1 hat, F3 hat, and F2, because of the multiplicity factor, is F2 squared. Okay, so starting with this, we are now going to apply 1 and 3. So the 1 makes this 1 into a 2, and the 3 makes this 3 into a 4. And then we are going to apply the F2, the virtual F2 operator, which is really F2 hat squared. So we act with F2 hat twice, so that makes this 2 and this 2 into a 3. And then finally, if we apply again the virtual crystal operator F1, then this corresponds to F1 hat, F3 hat, and it makes this 1 into a 2 and this 3 into a 4. So this is an example of a virtual crystal. And one important fact is that if you have two virtual crystals of, let's say, the same embedding, then if you take the tensor product of them inside the tensor product of the ambient crystals, this is again a virtual crystal. So under the tensor product, we keep the alignment. So now what I want to do is I want to apply this to the setting that we had before. So in particular, remember we were looking at the B spin crystal of type BR. So here I've taken a slightly more complicated example than before. So I'm now looking at the B spin crystal of type B3. So now I have a triple of pluses and minuses. My highest weight vector is plus, plus, plus. And then my Fi operator changes when I is not equal to R, acts if you have a plus in position I and then minus in position I plus 1, and then it just switches this to plus minus. So minus plus goes to plus minus, and an FR operator makes a plus in position R into a minus. And if you do that, then you get this crystal graph for the B spin of type B3. So because for these weight 0 highest weight elements, there's already a lot known for type C. what we want to do is now we want to model this B spin crystal of type Br in terms of a type C crystal. So the ambient crystal that I'm going to look at now is the vector crystal of type Cr, and I'm going to take the rth power of this. And so the embedding of thinking diagrams that we are going to look at is this embedding. So in this case, my multiplicity factor is 2 for every node except for the rth node. And my sigma just identifies, so sigma I is just equal to I. Okay. And so inside this crystal of type Cr, my virtual crystal will be the component of the highest weight vector given by 1 tensor 2 tensor and so on, tensor r minus 1 tensor r in this ambient crystal of type Cr. And well, the nodes will be all the nodes, so it will be r-fold tensor products such that they are weakly decreasing, and every value of the letter only appears precisely once. So this would be under the ordering where 1 is smaller than 2, is smaller than r, is smaller than r bar, and so on, is smaller than 1 bar. And for me now, the virtual crystal operators are just squares of the crystal operators in the ambient one. And for the rth one, they are exactly the same. So if we do that, then as you can see in this picture, right, our spin crystal of type B3 can be modeled by this virtual crystal of type C3. Okay, so all of this was just to sort of set the stage so that we can analyze the setting for the B spin or B vector crystals of type B in terms of crystals of type C when I start looking at the promotion operator and the cyclic sieving phenomenon. So now what I want to do is tell you more about the promotion operator on crystals. So this will be done in terms of what is called the crystal commuter by Enriquez and Chemnitzer. They introduced this in 2006. And this crystal commuter, which, sorry, I also call sigma, but it's a capital sigma. This will be given in terms of the Lustig involution. So the Lustig involution on a highest weight crystal of highest weight lambda maps the highest weight to the lowest weight, and it also flips E's and F's. So an Fi operator would be mapped to an Ei prime operator, where the prime, so for type A, for example, an Fi operator would go to an En minus I operator. But for type C, Fi would just be mapped to Ei. And then the crystal commuter, basically what it wants to do is it wants to take a tensor product B lambda tensor B mu and switch the two tensor factors. So it wants to go from B lambda B mu to B mu tensor B lambda. And what you do is you take each tensor factor and you act on it with this Lustig involution. So you flip those upside down, but then you also flip the entire thing again with this Lustig involution. So that's how the crystal commuter is defined. And well, if we now have a highest weight element in an n-fold tensor product of a crystal, then we can define the promotion operator by taking this crystal commuter, and we are going to split one of the tensor factors off and keep the other n-1 tensor factors together. So basically what this will correspond to is it will sort of rotate or move one of the tensor factors to the end. So let me do that in terms of an example. So here we are looking at the four-fold tensor product of the vector representation of type A1. So here's a particular highest weight element of weight 0, one that we have seen before, right? 2, 2, 1, 1. And to act with the crystal commuter, or to act with promotion, what we do is we want to sort of split off this element. And then we want to act with eta on this and also eta on the 1. So eta on 1 is just 2, because we are mapping a highest weight to a lowest weight. And the eta of 2 to 1 is equal to 1 to 1. Because again, this element is actually lowest weight, and so you're mapping it to the corresponding highest weight. So therefore, the promotion on this element will be, well, you take your eta of this factor, which is this part, and the eta of the 1, which is this part. And since this is actually a highest weight element of weight 0, you don't actually have to act again with the eta in the setting because it's already a highest weight or lowest weight element. So the answer is equal to this. That will be the promotion operator on this particular element. So what we want to do is we want to actually view this promotion operator as a rotation on what are called chord diagrams. So let me sort of explain what I mean by that, again, in this simple setting of an n-fold tensor product of type A1 crystals. So as we've seen, right, a highest weight element of weight 0 in type A1 is basically nothing else but a dig path. So here we would go like up, down, up, down, up, down. And if you look at the insertion under RSK, if you look at the recording tableau of this particular word under RSK, this would actually correspond to the standard tableau, a 2-row standard tableau. Or one way to look at it is the element in position 1 is this 1, then the element in position 2 is associated with a 2, so that should live in the second row. Then the 3 should be again in the first row, the 4 should be in the second row, and so on. So that's how you can also associate these elements with a 2-row standard tableau. For 2-row standard tableau, the promotion, there's another way of defining promotion, namely by removing the 1 and then using jeu de taquin to move everything down. So you can check that the promotion definition that I've given you in terms of Enriquez-Chemnitzer is the same as the promotion operator, where you remove this 1, use jeu de taquin to slide everything down, subtract 1 from every entry, and then add the highest letter again. So those two definitions of promotion actually correspond to each other. But what we now want to do is we want to view these elements in terms of what are called chord diagrams. And in type A1, the way that you can get a chord diagram is as follows. So you just write the numbers 1, 2, 3, 4, 5 on a circle, right? So basically we just view this as a circle. And then we are going to pair the one like two letters if they were actually bracketed in our original bracketing for the crystal. So in this case, right, 1 and 2 are bracketed, 3 and 4 are bracketed, 5 and 6 are bracketed. So we get this particular chord diagram. And then if we do that for the element that you get under promotion, then we, well, in this case, right, 2 and 3 are bracketed, 4 and 5 are bracketed, and then 6 and 1 are bracketed. So you can see that this chord diagram over here is just a rotation of the chord diagram over here. And similarly, there's also a promotion orbit of order 3. So this has 3 elements in it. Then the chord diagrams here look like this. And you can see that under rotation, if you just rotate the chord diagram, then the promotion actually corresponds to precisely the rotation of the chord diagram. So the aim of what I want to do is find something similar for B spin. Like what would be the possible chord diagrams that have this property that if we act with promotion, it will be just rotation on the chord diagrams. Okay, so basically what we are after is some theorem like this. If you have a map that maps a highest weight vector of weight 0 to a chord diagram, if you do that and then you do rotation, you want this to be the same as the promotion operator and then mapping it to a chord diagram. So for type AN-1, the adjoint and the vector crystal, and also for CN vector, this was in fact already achieved by Pfannerer, Ruby, and Westbury. And there are various papers where corresponding chord diagrams have been developed. And so what I want to do in this talk is do that for type BN, where this wasn't known yet, for the spin and the vector representation. So this is what we have done in this paper in collaboration with Pappe, Pfannerer, and Simon. Okay, so what I want to do now is sort of outline how our construction works. So how we can define a map from these highest weight elements of weight 0 to chord diagrams. And in fact, in the paper, we do this construction in two ways. One is by using certain fillings of promotion and evacuation diagrams. This uses certain operations that Christian Lennart has introduced in 2008. And this construction shows pretty easily that the promotion and rotation actually intertwine. So this property that we want follows pretty easily from this construction. And then the other construction uses four-mean growth diagrams. And this actually proves injectivity. And one open problem that we haven't answered yet is to actually show what kind of chord diagrams actually come up in this construction. So to actually show what the image is. But the chord diagrams that do show up have this rotational symmetry under promotion. And so the way that we are going to achieve this is by using the virtual crystal setup that are introduced at the beginning of the talk, because what we are going to do is we are going to sort of use this embedding of type B into type C, and then use what is already known by previous work by Pfannerer, Ruby, and Westbury to then get results for type Bn as well. So that's the plan. And in this talk, I will basically just, in terms of an example, tell you how this construction works, and then I will leave the details about this construction for you to read in the paper. So I won't actually go into details about the foaming growth diagrams. So let me tell you how we actually define this map. Using these fillings or the promotion diagrams. So here's an example. Here is a tensor product of type B3, the B spin crystal of type B3, right? So we have 3 tuples of pluses and minuses. So these elements are in B spin. And you can check that this is actually a highest weight vector and that this is also of weight 0. Okay, so this would be one of the elements that we are interested in. And so the first thing that we do is we map this to a sequence of weights. So we always start with weight 0. So when I write here 0, 0, 0, that just means this is a weight, and this just means weight 0. Then if we look at the rightmost factor, then, well, up to a 1/2 for the spin, this would be of weight 1, 1, 1. And then if we look at both of these, this would correspond to weight 2, 2, and so on, right? So looking at all of these, this would be of weight 3, 1, 1, and so on. So the first sort of row here in my diagram really just comes from the weights if we read our tensor factors from right to left and we look at the corresponding weights. Then the next line we obtain by doing promotion. Okay, so if we do promotion on this and we sort of offset everything by 1, then you would get the second line. And then if you do promotion again, you would get the next line, and so on and so on. And in this case, you can see that if we do the procedure 8 times, then the top line here is the same as the bottom line here. So this particular element here is in a promotion orbit of size 8. Okay, so that's step 1. And then the next step that we do is you actually look at certain elements in your, so certain sort of squares, or actually all of the squares in this diagram. And what you do is you take this weight plus this weight minus that weight. And you then count how many minus signs do you get. And these are these numbers that I've written here in the bottom. So for example, for this particular square, right, if I do 0 plus 0 minus 1, 1, 1, I get 3 minus signs. So that's why I have a 3 here. And you do that for all possible squares. And then the other thing that you do is you sort of take this part of your diagram and you just move it over to here. So that's why this actually becomes a square. Okay, and I have omitted all the squares where you have a 0. So when I don't write something, then that means you have 0 negative signs. Okay, so now we sort of have this matrix, And we now just view it, we erase all possible, all these weights, and we only keep track of these numbers that we obtained. So we get this this adjacency matrix, and it turns out that if you look at, you view this as the adjacency matrix of a graph, then this precisely gives you a chord diagram. So if we again write our numbers 1, 2, 3, 4, 5, 6, 7, 8 on a circle, then this matrix is telling us that, because this is in row 1, column 8, that 1 and 8 should be connected with multiplicity 3. So you could also view this as like a triple of connections. So this would be our chord diagram, and it turns out that under promotion, this chord diagram precisely rotates if we act with promotion. Any questions so far? Okay, so if there are no questions so far about the construction, then in the last couple of minutes, what I want to do is apply this to the cyclic sieving phenomenon. Okay, so because now we have the action of promotion on these highest weight elements of weight 0, and we want to study their orbits. So the cyclic sieving phenomenon was introduced in 2004 by Reiner, Stanton, and White as a generalization of the Q equals -1 phenomenon by Stembridge. And the setup is as follows. So you start with a finite set, which I'm going to call X. And then you have a cyclic group generated by some element C acting on the set X. And zeta will be the Cth root of unity. So where C, this is just the size of the cyclic group. And for the cyclic sieving phenomenon, you also need a polynomial with integer coefficients in the variable Q. And then Reiner, Stanton, White defined this triple of the set, the cyclic group acting on the set, and this polynomial. They say that this triple exhibits the cyclic sieving phenomenon. Well, if the size of the fixed points under the action of C to the D is precisely this polynomial evaluated at this root of unity to the Dth power. And we want this for all possible D. So if that is the case, then we call this a cyclic sieving phenomenon. Okay, so basically, this polynomial, by evaluating it, tells you something about the orbit structure of this cyclic action. Okay, so what we want to do now is we want to find a cyclic sieving phenomenon for the cases that we have looked at. So we looked at the vector representation of type C, which in terms of combinatorial objects was also given by oscillating tableau. And then we also looked at tensor powers of the B spin representation of BR, and the combinatorial objects associated to that were R fans of Dick path. And the cyclic action on this that we want to look at is the promotion action that I've defined for you. So what we now need to find is we need to find polynomials FQ that have this property that if you insert a root of unity, it actually counts the fixed points. And it turns out that one way of of getting such a polynomial is by using what is called the energy function. And again, one thing that I've worked on a lot with Professor Okado was to study the energy function in various settings. So what do you need for the energy function? Well, first, for the definition, you need the local energy. And the local energy is actually defined on an affine crystal. So far, we've only studied non-affine crystals. But to define this local energy function, you need an affine crystal. And so the local energy is actually defined in a more general setting, but here I'm going to restrict myself to the tensor product of two equal crystals, so B tensor B. But you can also take two different crystals, B1 and B2, and also define an energy function. So this local energy function is constant on classical components. So this is equal, so HEI B1 tensor B2 is equal to H B1 tensor B2 when I is not equal to 0. And when I is equal to 0, then it can change by plus or minus 1 in certain settings. So now what I want to do is take the setting that we had before. So we looked at the vector representation for type CR. And it turns out that there is actually an affine version of this crystal. So there's a particular Kirillov-Reshetikhin crystal for this, where you also add this 0 arrow. And for this very simple kind of Kirillov-Reshetikhin crystal, it's easy to write down an explicit formula for this local energy function. Namely, if you order your elements like this, so 1 is smaller than 2, smaller than R, is smaller than R bar, smaller than 1 bar, then this local energy function is equal to 0 if the elements are weakly increasing, and it's 1 if there is a descent when A is bigger than B. And similarly, for the B spin crystal, you can also look at the affine version of this, and there's an explicit formula in this simple setting. If you look at the local energy of a highest weight element in the tensor product of two such things. So if you take plus, 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 tensored with another spin element, then the local energy basically counts the number of minus signs in the second factor, plus 1, and then you divide by 2, and you take the floor of that. So there's an explicit formula for the energy function for this, or the local energy function. So now the energy function itself can be defined as follows. This will be the sum of I from 1 up to n minus 1. And this is sort of like an analog of the major index in this case. So yeah, you basically sum up the local energy functions up to this factor. So this is an analog of the major index. And then the polynomial that we want to look at for the cyclic sieving phenomenon is basically the polynomial where you sum over all highest weight elements of weight 0 graded by this energy function up to some constant, which I'm omitting for this talk. And then it turns out that if for your set X, you take the set of all highest weight elements of weight 0, if B is minuscule, so we need to assume this for the theorem, And if we take this, the cyclic group to be the action of the promotion operator in this case, then with this polynomial that I've just given you, the claim is that this actually exhibits a cyclic sieving phenomenon. And the proof basically uses various papers. Namely, it uses a paper by Fontaine-Chemnitzer, where they proved that certain cyclic sieving phenomena exists when B is minuscule, and then you have to combine it with some other results to actually show that the polynomial that you get is given by this energy function polynomial. Okay, and then in the last thing I sort of want to mention is that there is actually another polynomial that you could use in the case of type BR. And this polynomial actually also appeared in work by Sam Hopkins. And it turns out that this polynomial also gives you a cyclic, or I mean, conjecturally gives you a cyclic sieving phenomenon, but the polynomial is actually different from the energy function. So the polynomial that I claim also gives you a cyclic sieving phenomenon is this. So it is some Q deformation of the number of R fans of Dick path. So if you take this without this Q deformation, this is actually the number of R fans of Dick path. But if you Q deform it, it gives you, well, a polynomial in Q. And yeah, the claim is that this polynomial also works. But if you compare the two polynomials, so if you compare the polynomial in terms of the energy function, F32, then this would be the polynomial. If you compute G32, you get this polynomial. But you notice that if you take this modulo Q to the 6 minus 1, then the two polynomials are actually equal. And for the cyclic sieving phenomenon, everything, I mean, since we want to insert the sixth root of unities in this particular example, right, if two polynomials differ by this, if they're equal mod Q to the 6 minus 1, they actually give you the same cyclic sieving phenomenon. So in particular here we have a Q to the 12, but mod Q to the 6 minus 1, right? This makes up for this difference here, where here we have a coefficient of 3, and here we have a coefficient of 2. So it would be interesting to see if one can actually prove that mod Q to the, in general, Q to the n minus 1, these polynomials are actually equal. And that's all I wanted to say for this lecture. Thank you very much.
Thank you very much. Are there any questions or comments? Yes, Travis?
Ayana, have you looked at, okay, so R fans of Dick paths are naturally in bijection with reverse plane partitions in a square of with max height R, which also has a crystal structure on it, a type A, that you can actually promote up to affine type A. And I was wondering if the cyclic sieving phenomenon that you're seeing there is related with this promotion coming from the affine type A.
Yeah, so actually, if you look at the work by Hopkins, he actually looks at plane partitions, and so when he wrote down this particular cyclic sieving phenomenon, that's exactly where it was coming from. But yeah, your suggestion of actually looking at the crystals on those, yeah, that I haven't yet looked at, and that's a very good suggestion.
Thank you.
Any other questions? Yeah, I have one question. For the Dick path case, there is some homomorphic phenomenon that appears
Ah,
by German terminology. So as
yeah,
a
okay.
similar kind of statistics that shows us homomorphy
Uh-huh.
on their crystal sense.
So which work exactly by
Uh,
Roby?
Roby and Prop. Yes,
Yes,
they
okay.
gave us some the simplest case for Dick path.
Uh-huh.
Yeah. So I'm wondering, is there any similar phenomenon occurs for the B spin case or something?
Whether there's some homomorphy.
Yes, right.
Yeah, I'm not sure. So you want something where you have some sort of statistic that is
Right.
constant on orbits of
Orbit, yes, right.
Yeah, that's an interesting question. And again, I haven't actually thought about that. Yeah, that's a good suggestion.
Okay. Yes.
So one other question, have you looked at what happens for promotion for the type B under Borella insertion?
No, again, that's something I want to do and I haven't done that yet. Mhm.
Right, thank you.
So Masato is asking, in some cases, there's such a sieving phenomena is in affine real algebra character, or completely different, because you also use energy function and the tensor product. So can you say something about sieving phenomena among affine real algebra characters?
But so this would be the character for the affine.
Affine, yeah, affine.
Yeah, so in this case, it's not actually on the affine. But okay, so you are saying, so what is the action in that case? What is the cyclic action in the case that you are referring to?
Well, I'm asking other generic question, so
Okay.
my question is not well defined.
Okay. Okay, but you're saying that if one looks at the affine characters, then there are also cyclic sieving phenomena related to them. Yeah, okay.
Yeah.
Mhm.
Okay.
Okay. Any other questions or comments? If there are no more, then thanks, speaker again.
Yeah, thank you.
Thank you very much. And we'll resume at 11.